presentaba con Juan Gabriel Ramírez. Juan Gabriel es profesor asociado de la Universidad de los Andes, en Bogotá. Él comenzó su trilha científica, académica en la Universidad do Vale, en Cali. Ahí él fez un doctorado, sanduíche con la Universidad de California, San Diego. Aí terminou o doutorado, ele foi fazer um pós-doutorado também na Universidade da Califórnia, San Diego, até que ele foi contratado lá na Universidade dos Andes no ano 2015. Ele trabalha em sistemas fortemente correlacionados, dispositivos quânticos, materiais quânticos. Ele faz tanto caracterização de materiais como síntese de materiais. Ele fez um pós-doutorado na Universidade da Califórnia também, estudando materiais supercondutores, caracterização de materiais, novos materiais supercondutores. No ano 2015 ele foi contratado na Universidade de los Andes, onde ele montou seu próprio grupo e laboratório nos sistemas magnéticos. Ele trabalha com todo esse tipo de sistemas. No ano 2018 ele foi fazer um ano sabático também na Universidade da Califórnia. E agora ele está nos acompanhando aqui 5 meses, está com um professor distante. Então ele vai ficar mais 2 meses aqui. Quem quiser consultá-lo, pegar um contato e falar com ele depois também, você pode contactar ele. Então vai ficar mais 2 meses aqui no Instituto, ele é financiado pela FAPESP, com o programa professor visitante. E acho que só isso, só uma coisinha a mais. A partir de agora tudo vai ser filmado, tudo está sendo filmado, todas as intervenções de você também serão filmadas e serão disponibilizadas no canal do YouTube. Então, por omissão, você está autorizado a disponibilizar essas informações no canal do YouTube. Sim? Bom, Juan Gabriel, you can start.
Thank you. I think that you need that I'm yet still learning Portuguese, so
ele não sabe falar português.
so I will try my best. I'm still learning. I hope that I can speak a little bit more by the end of my stay here. But yeah, but feel free to ask in Español or English. So thank you everyone for being here. Thanks for the kind invitation to be here as a visiting professor and to give this talk to you. So I'm going to, I think I have a little long presentation, so I want to be kind of optimize the time. So I'm gonna jump into the idea that I want to present. So this is the outline that I'm proposing to discuss today. As Diego said, my research is mostly around systems that they have a strong electron correlation. That's the idea, and I figure that for some of you that might not be that clear exactly what an electron correlated system is. So I'm going to try to spend a little bit of time trying to explain exactly what I mean by electron correlations. That's kind of I think it's kind of important to actually give that context. I'm going to give you some example of materials that actually show those correlations that I'm going to be focusing on. And the idea here will be to show you what happens when you introduce disorder in those materials. And this actually is something that I kind of very involved in. So try to disorder a correlating material to see how it responds. That's the bottom line here. And then something that also I like a lot is studying the dynamics. So I have done different types of dynamics studies, transient, so looking at the temperature, the time, how things evolve. But I decided today to talk about the dynamics in the magnetism. Okay, so if anyone else is interested in this type of subjects, we can discuss later the other things that I have been doing. Okay, so this is the group back in Colombia. So this is from 2 different times. This is before the pandemic, actually. Some of them still are around. And then some of them actually are here. So Carlos is actually sitting here. He is staying here also with me for a few months. And then Alexander, he was here also a few years ago visiting. And then Diego also, he's coming also in a month working. He's going to work also in the lab. So this is the lab, the collaborators.
You need to click on OK.
Oh, so it hasn't been. So I have to go to the other screen. Let's click OK.
Turn off the button.
Is that okay?
Yeah.
Yes. Excellent. Okay, let's move. Perfect. Okay, so then research lines. So in working in more or less like if you have an electron, a correlated system, one thing that is kind of difficult to see is what is the length scale of the correlations. So length scales are very important because different correlations, they have different length scales. So one thing is to go and explore different sizes of your material to switch on or off some correlations, and then you will see what is the importance of one versus the other one. So you do that with different type of approaches. I decided to go into nanoparticles, so we screen our systems and see how they behave. So this is something that we have been done. This is a tomography done by X-rays. So this is a coherent diffraction imaging with Bragg peaks. This is an AFM of particles. And then the other thing that we care about is the multi-computing kind of physics. So here the idea is that you turn or you try to look for materials that behave as neurons or synapses in the brain. So we have a lot of research going in that direction, but I'm not going to talk about that much, just a few things. And then other lines that I've been exploring in my lab is with optics. We are kind of trying to see or look for functional photonic devices, hard magnetic materials, and high entropy oxide recently. So this is something that if you particularly have interest in any of these subjects, let me know. So what's going on with the typical material? So what you have in a 1 centimeter square, a cubic meter of matter is that you have a bunch of atoms. In any atom, you have a bunch of electrons, and then there is a lot of correlations between the electrons in place, right? So the motion of every electron is somehow subject to the presence of these other ones, okay? So that's what real physics is. So one way I like to think about this is thinking about in a highway, for instance. So you have cars here being the electrons in a system, for instance, and then a system that we think about with no correlations at all may be something that is close to an ideal gas, for instance. So if a car, for instance, decides to stay here to stop, then nothing will happen. The cars behind will have enough time to be aware of that they stop, and then they will find a way to kind of go through it. So nothing will happen kind of important in the system. Then the other extreme is where there is a lot of correlation. So there is the electrons are so tight that they cannot move. This is something like that. Think about cars. This is either, I always say that this is Bogota. So there's a lot of traffic, nothing moves. So this is a system with high interaction, high correlations, okay? These systems are also, in a way, at least in my view, not very interesting because there is nothing you can do. If you take a car out, nothing happens, right? So then interesting things will happen when you are in between these two. So when you have something that is, you can move very fast, and then if a car decides to stop here, then something dramatic will change, right? So something will happen for sure. And this is, to me, the best way to explore electron correlations in a system, okay? So what I want to look for materials that every time I take an electron out, something dramatic will change. That's the bottom line. So the idea is how you can study these kind of systems. So which ones are they, how I can build them, and then how can I actually take an electron out of the system? This is something that I want to hopefully show for you. So then let's go back to the idea, the fundamental idea of something that is not correlated. And then we have to go to the band, typical band theory of solids. All of you probably know this a lot. So then you have one particle that actually forms like bands, and these bands separate the electrons. And then you have, just by looking at this, by modeling an electron as with no correlations at all, or doing some sort of a renormalization that actually can be applied to one electron, then you can explain all these kind of materials. You can explain why a conductor is a conductor, insulator, or semiconductor. And this has been done for many years. from the beginning of the transistor. So here, when the transistor was invented back in 1948, so the idea was to understand how the electrons move in an oxide or semiconductor in this case. So, and then from here, this moves into building transistors, electronics, and everything that we have and we also find, okay? So, what happens in something that is not a highly correlated system? So, something that is not either a semiconductor, a conductor, or insulator, okay? So, if a material has an insulating property, then basically this will be something like the resistance as a function of temperature. You know this, and this is basically can be derived by the band theory that I just showed. So this is an exponential decay. So if the material is a metal, then it should have something like this. In this scale, it doesn't look much, but it's actually proportional to the temperature, so it has a positive slope. You all know this, okay? But then something that cannot be explained by band theory is that you can have something that behaves like an insulator, and then at high temperature behaves like a metal. This cannot be explained by assuming that electrons are independent. In log scale, this looks like this, and then the idea here is that you have a metal insulation transition. You have, well, in this case, this is an example of an iron oxide, V₂O₃. This is a thin film, 100 nanometers. I'm going to explain it later also. But then there is a lot of things to talk about. This is actually one of the reasons for the talk. So what happens in the material? So it has a hysteresis. So if you go back in temperature and then you reduce the temperature, so the transition temperature is not the same, and this is because there is a phase transition. It's a first order phase transition. This hysteresis is a signature of coexistence of different phases. It's a signature of metastable states. Okay. So that's the idea of that. The transition temperature here is kind of high, 300 Kelvin, 68 Celsius. There is a structural phase transition. It goes from a rotile here in this high temperature, and then it becomes a monoclinic at low temperature. This is a non-magnetic oxide, so there is nothing magnetic here in principle. Okay, the distortion is about 1%, so 1% volume change, so it's quite big. So this happens because there is a dimerization between these vanadium atoms. Just when you change the temperature, and then actually try to understand the physics behind, or the reason why there is a phase transition in this material is still, even though many years ago, still an open debate. Okay. There is another vanadium oxide I'm going to talk about today, and this is is from the same family. This is V₂O₃, so this is another vanadium oxide. This one also has a metal insulator transition. It has the transition at low temperature in this case. The difference being that at low temperature is an anti-ferromagnetic material. So it orders as an anti-ferromagnetic. At high temperature, it's just a paramagnetic metal. And then there is also this hysteresis coming from the structural phase transition that occurs. So at high temperature, the symmetry is rhombahedral, and then the structure is more clinical at low temperature. And you can see here there is a huge change. This is for just one particular graphic. And this is how we use to map the structural phase transition. You see that in between, you have the two contributions of the crystallographic phases. So there is both a structural phase transition and a metal insulator transition. I spent many years trying to understand if there was a difference in temperature, trying to see if the structural phase transition was the one that was driving the metal insulator transition, or the other way around. And so far, we conclude that these two happens at the same temperature. We don't know which one drives the other one. Okay. So just to give you an idea for the students, I'd like to show this image that summarizes the metal insulator transition compounds that they are somewhere there. In case that you are looking for something interesting to research, then all of these has some sort of high electron conducting materials. They have a metal insulator transition, and they have some sort of a structural phase transition as well. Okay. So where is vanadium oxides? There is a bunch of vanadium oxides, V₃O₃, V₄O₃, all of these are the magnetic phases of vanadium oxides. Okay, so vanadium V₂O₃ is here, and then the V₂O₃ here is the one I'm talking about, and then there is this other material that I'm going to introduce later. The manganite, PCMO, is at 80 Kelvin. It's not in this chart because the physics is somehow different, but it will be somewhere there. Okay. So how do we measure correlations? So here is a kind of a well-accepted way that was proposed by Dmitry Basov. So the idea is that you measure the kinetic energy of the electron using something like DFT, for instance. You calculate the DFT, you measure how much the kinetic energy will be. DFT with not including any kind of electron-electron correlations, and then you go and then measure the kinetic energy with some optical type of experiment, and then the ratio between these two, how different they are, is basically how correlated they supposed to be. So in this is where you get the most correlated materials. Here's where they don't. Basically there's a match between the two. So vanadium oxide, V₂O₃, is over here, so it's somehow correlated. V₂O₃, I am afraid my this one here, the open one, is highly correlated. So these 2 points here are the 2 vanadium oxides. They're supposed to be vanadium oxide is supposed to be somehow similar, but somehow the difference between these two are, the difference in correlations are kind of, in principle, they are big difference between the two. I kind of also try to focus on these differences as well. And then there is a lot of manganite, this type of, I actually not sure the name of this, but somehow there are perovskites also, instead of manganite, they are using strontium, and then there is a lot of correlations here as well, as you can see. And then nickel oxide somehow, even though seems like very naively speaking, like should be trivial, is one of the most correlated oxides that there is. There is reasons for that. Okay, so how do we go and measure correlations? This is something that at least when I was a student, I was always asking, and there is no clear answer. But I will propose a way to kind of show it to you. So one way that I came up was to disorder the material. So you have this film here, and then you actually just back in the analogy with the highway, so you take out electrons somehow. You disorder locally the structure. So how do you disorder this? You induce some radiation damage. You send ions with a particular energy, and then you knock out some atoms, you create some vacancies, you create some dislocations, and then you can actually tune how much dislocations or disorder you can create in the material. Okay, this is the profile of where the ions end up. So as you can see, the most of the oxygen ions end up in the substrate, so they just go through the vanadium oxide, and then so my point here is that the damage you are doing is very tiny, as I came at the beginning. Okay. Actually, this is a curve that we calculate. It's not like just a drawing. We calculate this profile, and then this is basically the idea here. So let's focus on actually what happens. I don't want to go into too many details, but then the idea is that the transition temperatures of the vanadium oxides, V₂O₂ and V₂O₃, they move a lot. So they move a lot in V₂O₃. They don't so much in V₂O₂. Somehow this is telling me that the degree of correlation of the two is not, there is a huge difference between the two. So if I look into the change in the resistance before the radiation and after the radiation, what is to me most amazing is that the resistance of the material, both V₂O₂ and V₂O₃, gets better. So you have a material that you disorder, and somehow it becomes more metallic. That's, to me, if you think about what is a metal, that doesn't make sense, right? So if you disorder something, then it becomes more metallic. But that happens. It happens even more in V₂O₃. So it makes kind of sense for what I showed just before, the degree of correlation between V₂O₂ and V₂O₃. So here, I'm just proposing a way to actually go to the lab and then measure how much correlations are in a material. So this is the state here. Low high temperature for both oxides is a highly correlated state. Yes, and this is a proof of that. Okay, enough. So now back to the lab, and then now what we do with this. So then the idea that we have is the following. So now we have a system that has spins, photons, and electrons, and then the idea will be to couple, and they are coupled already, right? So then the idea will be to try to turn off or on some of these interactions and see which ones prevail, which ones disappear, and so forth. Okay? So this is kind of the idea. So how do you do that? You can do this by fields, either magnetic fields or electric fields. You can do this by light. We have actually been doing some experiments just here with light, for instance. We can do it by strain, so we can put this in a pressure cell and then squeeze, or some sort of a similar experiment with pressure. So then you will see some differences. And then with proximity effects, this is something I'm going to talk about today. And then the idea is that how we can control magnetism here. So how can we control magnetism using all these external stimuli and use it as something useful? That's what I want to say. So I'm going to focus in proximity effects. Proximity means that if you put one material next to the other one, the properties that emerge are somehow different from the properties of each material by itself, right? That's it. Okay, so this is very kind of dense, summarized, but I'll try to go through. This is an image of an experiment that is called SNOW. It's a scattering of near infrared. And the idea here is the following. Every pixel here is telling me if the material is or not an insulator. So the blue color means an insulator, the red color means a metallic pixel, okay? So this image was took at 173 Kelvin, which is at the middle of the transition of V₂O₃, okay? And this is something that you expect. You are in the middle of the transition, so you have the coexistence of both phases, the insulating phase and the metallic phase. But what is strange is that this coexistence somehow arrives in a very kind of well-defined pattern that you can see here, which is somehow connected to the way that the crystal structure is changing at the transition. Okay, so the details, we can discuss the details, but the message here is that there is a coexistence of the two phases from the conductivity point of view or the resistance point of view. There is something metallic coexisting with something insulated. So this is a close up. You can see the domains. We study all the things that you can imagine here. So we study the perimeters, we study the correction rate on the domains, we study how they change it and change the thickness of the sample. If we go, because this is somehow a percolation kind of effect. So we went to 2D to 3D percolation systems. We did all of that, and everything shows, I mean, points to a percolation phase in this material. But we did also something that is not that easy, and is to measure the same idea, but with the structure. So what I was kind of pursuing is that I wanted to know if here in this region, the crystal structure was exactly the structure that corresponds to high temperatures. Okay, so the domains change in size, so we needed a proof that can go to very low pixel size. So we went to recently by the time of the experiment, 2018. So we went there and then we measured this line in the ATS in the synchrotron in US. And then we measure the structure at with a size of 20 by 20 nanometers more or less. Okay? So every point here, every pixel, is a color that was decided by which of these two peaks are higher. So this is a 2D image of the synchrotron. You see the each peak is the high temperature phase, the low temperature phase, sorry, the high temperature phase. And then you see that for every pixel, both phases coexist Okay, at the same in the same 20 by 20 nanometers, which is amazing. So basically, here we say that this is higher in percentage, and then we give this pixel a color blue in this case. Okay, then you have this image of colors that tells you which phase is most predominant. Okay, and then you can see that there is a spatial distribution of phases that are somehow related, I mean, in the same length scale of this experiment. So there is a phase coexistence in the resistivity part, resistance part, and then there is a coexistence of the crystallographic part. So, this is something for some of you that might not connected yet. So this is somehow, at least in my mind, it's exactly similar to a first order phase transition, which is here seen as this experiment. This is a supercooled water. You probably saw this many times. You probably have done it. Let's see if it works. Work. Yeah, I was expecting that. No? Okay, you've probably seen this video already, right? So basically you shake it and it freezes, but the freezing, of course, nothing is, did something happen while I was? Anyway, so it becomes ice, okay? And then there is an interface between liquid and solid, and that interface is moving through the whole to the whole volume of the sample, right? So it's exactly the same. So we are looking at the interface, and just in the interface there is a mixture between these two. And then what we are doing here with these techniques is looking at the interface. So at the interface, wonderful things happen, as you may see. And then this is something we wanted to do: go to the interface of the transition and then use it for something interesting. The first thing I came up was to put vanadium oxide next to anything. And the first thing we decided to do is just put on top of it metallic ferromagnetic material, something that is very soft, mechanically soft. So then you put nickel. So what is going to happen here, you may ask? So here is the standard thing that you can do. So you go there to your DSM, and then you measure magnetization as a function of the field, and then you see how the hysteresis curve looks like for your material. And then you increase the temperature just to go through the transition of iron oxides, and then you see that this is kind of increasing, which kind of makes sense. And then at some point it's huge, and then it goes back, and then goes back again, and then it stays there. Okay, so it's going to, the coercivity is going up, and then it's going down, and that in principle doesn't make sense because nickel, we never do that by itself. We actually compare the coercive field with just nickel. So this is the nickel, it's a straight line, and this is the heterostructure that I just shown there. So quite different. They only are similar at the high temperature, and this is because we grew the nickel in top of this material at room temperature. So you have a 300% of change. And this is very useful. We wrote a couple of patterns just to kind of thinking about how to use this for something useful. And I can talk about that later. But anyway, so then here the idea is that, okay, we can control the magnetization with the static magnetization just by changing something. So what's going on here? We actually, we kind of try to explain it. We did some SPUNF simulations. So those simulations basically to simulate what will happen when you break into domains due to the strain of the vanadium oxide. So basically the idea is that because you have different domains, different crystal structures, then every structure will change the nickel in a different way. Then you have a gradient, right, of strains. And then just in the interface is where you actually have the most stress film because you have a bunch of interfaces. And that is exactly why it's higher just in the middle of the transition, and then it's different at higher or low temperature. That's kind of the main idea. So the purpose of today's talk, almost 37 minutes, is that we wanted to study the dynamics. So what I mean by dynamics, so if I have a tiny magnet, and then I apply a magnetic field, something that you may know is that this guy will align to the magnetic field. Okay, but then what is some students don't remember is that actually that will never happen if there is no something that dissipates inside the material. Okay, in principle, nothing, if you work down the mathematics, this should actually oscillate all the time. But then when you add some dissipation, then this will actually align perfectly with your magnetic field. Okay? At what frequency, or what is the frequency of the oscillation of that? It's actually omega 0 and depends on the nature of the spin structure, the electron itself. And then the idea here is that I want to maintain this oscillation, and for that I have to actually apply an external microwave magnetic field. And I do this with microwaves because it's close to the natural frequency of the electron. Okay? So when I do this, then the system will precess forever. And then that precession is kind of useful because then if I match the frequency between the two, then I will have a resonance. Okay? And in the resonance process, so what is going to happen is that the electrons, and this magnetic moment is precessing a lot, the amplitude increases by a lot, then it will, so I can use it to map the neighboring spins and then get information about the environment, the magnetic environment of my system. That's kind of the idea. But more into that is that actually what I wanted to do is to put something between, so something close to the magnet, and then see how this oxide will actually change the dynamics of the magnetism. Okay? What we found is that actually there appears like two resonances, actually, something like this, I will show. And then this was kind of a novel discovery, very interesting and very useful as well. Okay, so then this is just technical, I'm gonna skip it, basically just to show you that these interfaces are good. We don't have much roughness between the layers. So we cannot blame, whatever I'm going to show you, we cannot blame it into the samples that are not good. That's kind of the bottom line. We can go through this if you have questions. We can come back to this if you want. But here, I know that there is many experts here in this setup, but the idea here is that we measure a bunch of resonant curves. This is the derivative of these Lorentzian curves. This is the resonance that I was talking about. But in the experiment, we measure the derivative of this. So this curve, and I'm going to show you a bunch of this. Okay, but I'm going to plot it in a different way. I'm going to use this, and then I'm going to add another axis in this direction, and then you're going to see this from the bottom, from the top. So this will be red, and this will be blue. Okay, that's the. Oh, here you have the resonance. So we did some. This is just for the students. So by looking into what is the resonance, so at what field you actually get a resonance, you will gain a lot of information. If you put your energy, your free energy, and then you can work out what it will be the resonance frequency, and then you can check. You can actually check what is your magnetization, and this magnetization here, it has inside all the interactions that you can think of. Everything that happens in the sample will be in this parameter here. Okay, this is thanks to Kittel, that was the one of the pioneers of the FMR and EPR techniques. So you can put all these energies into your free energy equation, and then you can see effects of changes in the crystal structure, the crystal field, for instance. You can see how the sample, if I take a ferromagnetic metal and then I deform it, if I compress it or expand it, the magnetization will change. And I can see those changes also because the resonance field will change. And kind of more interesting is that you can see even magnets. So you can see how these other spins change or the coherence between the neighborhood, and then you can see that there is a spin wave that actually is traveling in this direction. Okay, so all these things can be learned from fMRI. So the result are the following. So by looking into this geometry, so this is the sample, and then I apply a perpendicular magnetic field. So I get something like this. At high temperature, I get just one single resonance. Okay. In between, just in the transition, I get something like this. There is two resonances. And then again, the question will be why there is two resonances. And this is only this is only happening in the oxide. This is the nickel only, and this is the nickel with the oxide. If I plot all the temperatures as of this particular sample, and then you will see that this line here that is kind of white is kind of a straight line, more or less, right? And then you have something in between, something that this is the kind of the line that actually matches exactly the nickel. But then we see something like this. So we have an anti-crossing kind of behavior. So there is something like with some magnons that they are scattered between them. And then this happens because the sample is highly disordered from the crystallographic point of view. But that disorder is traveling through the nickel film and is creating defects in the nickel. And the interesting part is that those defects are reversible. So I can go back, forward, and then I can create those defects again every time I decide to change the temperature. Okay? So just to summarize this very quickly, we have actually looked into a way to calculate the phase fraction of the two resonances. So I can actually account for how much is the first resonance versus this one, and then somehow make like a phase fraction. So how much is this versus this? So at high temperature, this one is the higher, and this one is 0. And then at low temperature, this one is the maximum, and this one is 0. So I can actually plot as a phase fraction. So I will call this the high temperature phase and the low temperature phase. If I do the same at the same temperatures, but looking at the X-ray diffraction data, then I can do the same with the diffraction. I can see how much is the proportion of the high temperature peak and the low temperature peak. And then I will know a structural or a phase, crystallographic phase fraction. And then if I plot both of them in the same graph, I get something like this. They match perfectly. So what it's telling me this is that whatever is driving this is related exactly to the crystallographic structure of the vanadium oxide. Okay? Then we did some in-plane studies. So I apply now the magnetic field in the plane, and if I apply it in the plane, I see different stuff. I see the how the crystal structure, basically the symmetries of that appears when the phase transition occurs, right? So I see all the crystallographic things. So for instance, at low temperature, you see that this is exactly 4-fold, but at high temperature, it's kind of 6-fold. So you have something that is 6-fold and 4-fold. And what you are looking here is an angle that is the in-plane angle. So I'm rotating the sample this way, and then the sample, if I rotate it 4 times, I get back to the same place. Okay, that's basically the symmetries of the material. This is connected to the symmetries of the crystal structure of the structural phase of the phase of the vanadium oxide phase. Okay, I plot here the resonance field, so the field at which the resonance occurred, and then how big the resonance, how big the transition is. So the first one here, those maps are the resonance, and you see that there is matching this kind here, right? So you have this 4-fold, and low temperature you have this kind of 1-fold, 2-fold actually, 2 axes here. But then there is a rotation of 45 degrees between the easy axis of the nickel sample. So I have an easy axis where the magnetization wants to align at high temperature, and then at low temperature, it rotates 45 degrees, naturally. Okay, and that's kind of very interesting. And we proved that actually was a local effect by doing, let me jump into this because I will not have time, by doing some eccentricity beam images. So we look into the domains, And then these are the domains. The yellow here is high temperature. The blue color here is the low temperature. And then you see that there is some domains, okay? And those domains, if you calculate what is the average angle of the domains, you will see that they rotate, as you can see here, more or less 45 degrees. Okay, so the average rotation of the domains. And that actually matches perfectly the FMR result. And then we were kind of very happy because somehow this is what we thought about from the beginning, that the sample breaks into domains. These domains are very tiny and they are not expected to be in a nickel film. If you take a nickel film and then you measure how big the domains are, they are huge, they are microns. And these are nanometer scale magnetic domains. So in a way, we are basically controlling effects in nanoscale by using the correlations in these oxides. That's the message here, okay? So we are basically controlling the FMR. This is the resonance field, and then just in the transition, you see that there is a lot of disorder. There is no coherent rotation of the domains. There is no single resonance line, so there is nothing here. So it means that there is no coherent rotation of the domains in the nickel. And if I plot the change, the line width is related to how disorder is what is the dissipation of the processes in the magnetic system. And then you see that this is huge. It means that a spin will precess here very fast, and here almost there will be no precession. So this is somehow a damping switch, I call it. Okay, so a damping switch means that I can spin the electron and then just freeze it in a way, kind of abusing of the language, but it's basically that's basically the idea. So we have a switch. Okay, I'm seeing that I have 10 minutes. I don't know how much time we have, but I kind of wanted to jump into manganese. 10 minutes. 10 minutes. I'll do my best. So this is another example of how we can do strange physics with correlations. Okay, I'm gonna try to explain the basics and just jump into the results. So in between I will skip. So manganese are interesting because they also have mechanisms of transitions. And if you change the composition, you can have whatever you want almost. You can have something that is paramagnetic, ordered, you can have an antiferromagnetic, or you can have a ferromagnetic material, depending on how you change the composition. Okay? So you have like a lot of degrees of freedom. The crystal structure here is a perovskite where you can actually change these two materials. You can have a trivalent air ion or a divalent alkaline earth ion. And then you can change this in a way that actually will affect this environment of the manganese, which is in the center. Okay, every physics that happens here, it happens because this octahedra is changing the manganese properties inside. Okay, that's the trick. And then here are the oxygen atoms. Okay, so then let me just skip this, and then so I have to explain two things. The system that I'm going to talk about is a mixture between two manganeses. Okay, so one manganese being lanthanum, calcium, manganese, oxide. And this one is very well known. It's for many years people know this material, and it has all these properties here. So it has this perovskite structure. It has a spin A-type ordering, so the spin has a well-defined spin structure. And then you will see a bunch of these diagrams. I'm trying to put here the manganese ions with the orbitals, and then this is the way that they are organized in the lattice. And then every time you see these dashed lines, means that there is an antiferromagnetic coupling. Okay, so here you have everything antiferromagnetic, and it changes depending on you change the whole doping, the calcium in this lanthanum in this material. Okay, so not only that, is you notice that there is an order of the orbitals here also. So there is an order of the orbitals, there is an order of the charges, and there is an order of the interaction between the two. So there's many things that are competing here. Okay, so if you have something that is in between, so 0.5 of calcium here, then you basically add a way to control the material. You can by putting by controlling the distances between the two, which is what you do when you change the ion here, then you can change the interactions, what they say. Okay, so that's the idea, and then you can have something that is metallic insulator, ferromagnetic metal, depending on what ion you use. Okay, so then you have something like this. You have, let's say, x now being 0.3, and then what you have is okay, something like that. So you go from something that is every antiferromagnetic, because you have half of the ferromagnetic and antiferromagnetic. You have ferromagnetic coupling, antiferromagnetic coupling, and both of them are exactly half. You go to something that is not half, and then you may have, here's everything, and then you have something that is half ferromagnetic, half antiferromagnetic. When it's ferromagnetic, then you, by double exchange, you can have an electron that is jumping between manganese via an oxygen in between. So you can have a mobility, electrons moving through the oxygen by double exchange. So you have something that behaves as a metal, even though it's in a matrix of an antiferromagnetic material. So that's why this is interesting. This gives rise to many things. It basically breaks down, as you can see here, into small domains. So you will have the sample naturally will organize in a way that there is products, regions where locally there is ferromagnetic metal, and then in the matrix is ferromagnetic, is an antiferromagnetic insulator. So now by adding praseodymium, in praseodymium happens something very spectacular. So basically you have your hold up in here, and then you may have a situation where you can have everything again like a mixture between ferromagnetic and ferromagnetic and or antiferromagnetic couple, but you can break the antiferromagnetic coupling by applying a field. Okay, because there is this praseodymium is in principle a smaller radius than the lanthanum, so you can do that by field. If you apply a magnetic field, look at this. You have a huge magnetic field. You have a huge change in the resistance of the sample. You have a metal insulator transition. So this material behaves as the vanadium oxides that I talked about, except that you have to apply a magnetic field. So you apply a magnetic field, you sweep the temperature, it does exactly the same. It has a huge transition in the conductivity. But that's not very useful because the fields here are up to even 6 or in the order of 6 Tesla. So that's not very useful. But interesting. So what I'm going to propose here is that we can make a mix of the lanthanum calcium that has these small domains, right? With the praseodymium calcium that has either something that is very metallic or insulated if I apply a field, and mix these two phases together, and what we get is something like this. So we get the metal insulator transition that we saw with the needle field, and then we have the phase coexistence of the metal insulator, the metallic phases and the insulated. So somehow mixing these two, it gets rid of the necessity of applying an external magnetic field of 6 Teslas. Okay, and that's the beauty of this. So this is the phase diagram, and the message here is that we were able to measure everything here. Okay, all these transitions. And we measure the dynamics. Just to give you a summary. Oh, so there is a bunch of transition temperatures here. So this sample has the most phase transition that I've never seen in a material. So it has something that is a charge ordered insulator. It means that the charges ordered in the manganese +4. Then it has an antiferromagnetic orbiting. This is the near temperature. Then it has a Curie temperature because then from the antiferromagnetic matrix emerge these ferromagnetic domains, and those ferromagnetic domains they interact, they grow, and then they order, and there is a Curie temperature for that order, and then there is a metal insulator transition. Okay, and then there is something here that are given from us, and we are actually trying to find out what's going on here. This is what we're doing right now. So there is this region that is very interesting, this fluid phase, and fluid means that in this region between the PC and the metal-insulator transition, the domains are like a fluid. And the definition of a fluid is that if you apply a force, the deformation is constant. Okay? It means that if you apply a field, the domains will move. Okay? They will move and they will grow and nothing will happen. It's like a liquid. Okay? And that is something very interesting. And of course, it has a bunch of dynamic properties because the same nature of a fluid. And then when the metal insulator transition kicks in, then you have a solid. So now wherever it remains of this liquid, it freezes and it solidifies. I'm speaking about magnetism. And then those domains are somehow freeze to the lattice and they don't move anymore. There is no dynamics, okay? And this is quickly what I'm going to show you right now. So this is the metal insulator transition of this material. No field is applied here. The zero field is this one here. And then you see that there is a huge metal insulator transition happening in the material. This is the dynamics of the magnetism. Okay, so what I said before. So we have here, now this is field, and now this is temperature. Okay, so here we are in the paramagnetic region. So the signal that comes from here is just EPR signal. So it's just the electrons giving you resonances. Then it enters to a region where we are sensitive here just to the ferromagnetic effects, just to be clear. And then we see the kicking of the ferromagnetic domains, and they start to grow, right? And then the resonance field gets higher, okay? And then at some point, it changes a lot. It changes the resonance field, it gets stronger, and then it disappears. There is no dynamics. And here is just a snapshot of every region. So here you have very beautiful resonances that changes in resonance field. Here you have the coexistence of two domains. There is two domains here, 1 and 2, for instance. And then here, there is no coherent rotation. It's the same material, we are just changing the temperature. Okay? So, what's the idea? We try to explain this somehow, and then this is what we can, for. So, basically, if you assume that this is your sample, you have ferromagnetic domains, they grow, they connect, they percolate, they freeze, you can reproduce the entire curve. And I probably will stop with that. This is the simulations. So this is our own simulation where we actually, when we grow the domain size, we shift the resonance field. If we account here for percolation paths of the ferromagnetic domains, those percolation paths, those domains, will give you several resonances, sometimes 2 resonances. And then here, because the sample is very metallic, then if you include the damping into the simulation, then you can actually decrease this by a lot. By just changing 1 order of magnitude, the damping, you can actually kill the whole resonance. Okay? And this is what we think is happening. And just to summarize, I don't want to talk about this much. Oh, just a second, because I want to skip a lot of things, but again, if you are interested in this, I can always talk to you. Just a second. This is very slow. Yeah. I was very optimistic that I was able to do this on time, but that's it. I can actually, while this is moving, I can just say that, so as a conclusion of the, oops, even better. Oh, is this? No. So the idea here, the message is that electron correlations give you a bunch of physics. We still don't understand half of what I just showed you, we are still doing experiments trying to see not only what are the correlations that are important, but also exploring new ways to use this or to actually make this useful. So we have some ideas for neuromorphic devices using either vanadium oxides and manganites, and we are very active on that direction. If you want to talk about that or discuss some projects, just let me know. And I think I will end up with that. Thank you very much. Please continue. Sorry.
Hi, yeah. Thank you everyone for the nice talk.
Thank you.
Questions, comments? Any questions? Yeah.
So, thank you for the talk. And in these two compounds, manganese and vanadium, obviously you have in the insulator phases or semiconductor phase, you have well-defined balances on vanadium and manganese. But when you go to the metallic level, can you explain a mixed balance?
Yeah, manganese is a mixed balance. It has a mixture.
Homogeneous balance, homogeneous mixed balance. Is it possible to get in the metallic state?
It is possible to have can you? I don't think I got the question.
Because in the case of metallic state, you have conduction electrons.
Yeah.
So when you have a conduction electron, you must start to get intermediate balance. So you cannot get any 3+, 2+, whatever, something intermediate balance. You can measure the X-ray absorption.
Oh yeah, yes. I haven't done that in well, vanadium oxide is not like that. Vanadium oxide doesn't have a mixed balance. It is 4+. But what is happening is that so it's a Pyros type of transition. So it's basically a deformation of it's a dimerization of the vanadium. So, but the balance is still the same. The manganite is more complicated, but yes, there is a mixture between manganese plus 3+ and 4+, and the whole physics of the material can be explained in principle by this mixture between the two. So the question is, how can you actually control this mixed balance? And what we're trying to show is that so one way is with the ionic gravity of the doubling, for instance, or even with some other external stimulus. So in the case of manganese, I was more to be honest, in the manganese, I still learning how to control the properties before trying to, I still trying to understand the whole physics, but everything can be explained by this mixture between the 3+ and 4+. So the metallics ones are coming from the 3+, the insulated ones, and in principle, you can actually locally measure the balance. This is something actually we discussed last week with a colleague here to do in the single term with the RIS. So that's something that.
Okay, questions? Yes, I have two questions. Many languages, okay? Portuguese, English, and Spanish. Right?
Yeah, yes, please. Just those three.
Thank you for the presentation. About the manganites, you said you explored its properties with different tokens and changing the hardware of elements. Did you consider to explore as a function of the strength in your theory?
Yeah, that's something I didn't have time to talk about. So the data I showed you was symptoms, but those things were provided by a friend in University of Florida. But we were trying actually to grow our own samples, and then so we decided to go into the first stage, which is growing the pellets, the bulk materials. And then we found a bunch of interesting stuff just in the pellets that I think I need to understand just before moving to teams. But it's true that because of the tolerance factor that I showed, so this is very, pressure or strain is something that changes dramatically the properties of all this. It's possible even that just the strain by itself gets rid of the idea of changing the doubling. So you can change, you can instead of doping, you can actually just change the strength. So one thing that I have in mind, and I did that with vanadium oxide. So we can grow you can grow the manganite in a piezoelectric substrate, and then just put voltage into the substrate, and then you will somehow mimic the same strength profile that in the doping. And yes, in the case of vanadium oxide, it works beautiful. I mean, you can change the transition temperature by a lot. We haven't done that yet in magnetics. And probably something that we kind of did with a colleague is that we bend the thin film, and we saw that just by bending the thin film, it changes the PC. That was measured in a synchrotron in Australia. But there is a problem. It's because in the thin film, something that I didn't mention. So in the thin film, for the manganite, lanthanum, praseodymium, calcium, manganese, oxide, the only substrate that works is something that has a strong paramagnetic signal. It's huge. It's ALN, I forgot the name. It's something that it has to be there just to be epitaxial, but it messes up the magnetic signal. Okay, so then that's why they went to the synchrotron with neutrons and then measured them. So there is some trade-offs, basically. So that was a long answer for your question, sorry. But yes, we can do that. We haven't done.
And in this case, so if we could you change this? Could you manipulate the strength only with the mismatch between the substrate and the thin films? So this is something that you could explore too, because I don't know if for this particular material, but for there are some magnetites where you have more strain changing the substrate than you can with other techniques. So this is something that you could explore, for example.
That's correct. It's just like the thing that I can interested of is just devices, switches. This is something that is being in my mind all the time. So if you grow this in a film with a specific value of strain, then it will be that, and that's it. So that's why I always think about wherever it gives me a strain, something that I have a node to kind of turn off and on. And this is kind of what I'm kind of trying to achieve with this, hopefully. But yes, that's something we certainly can do.
Thank you, Juan, for the inspiring talk. And I'd like to go into the devices that you just mentioned. And what is the property of the materials that you study that makes them compatible with neuromorphic computing? So there's I'm expecting an integrated fire.
Yes.
So where does it come from?
Okay, that's I didn't have a talk about that, but I'll show you. I show you a graph that it will give the starting point. Just a second. This is the graph here. This is not something I talk about. This is a BFO. It's bismuth ferrite. Okay, it's a ferroelectric, multiferroic material. It's kind of antiferromagnetic, ferroelectric at the same time at room temperature. Okay. Then what we did was to put some just the simplest thing. We just put some contacts on top of it, and then with a substrate that is conductive, we measure the current voltage kind of characteristics. Okay. So what we found is that if depending on the voltage that you apply to go to a certain value in current, the sample change, and then it changes in a way that is permanent, in the sense that think about a resistor. You put a resistor, you put a voltage, and then every time you increase the voltage, then you get a current, and it's a straight line, right? So here is not the same. It's basically you apply a current, so it's kind of a straight line, and then it changes, and it changes to a value of resistance, and then it never comes back to that original resistance value. The only way to get that value back is to go and apply a voltage which an opposite polarity on the other side. So in that way, this voltage here is a reset voltage. Okay, so then you have something that is on and off by applying this voltage, and this is exactly what a neuron does with an external stimulus, right? So this is just like one particular property of the neuromorphic computing. This is just, it's actually a memory, okay? But somehow it's similar. So in a neuromorphic system, you have neurons and you have synapses. And one has memory, the other one does not. So what's the idea there? So the idea is that the idea is create something that has either memory or not, and combine them, and then do some, and simulate a neuromorphic, like a neuron kind of thing between two, like a real brain, right? With two neurons via a synaptome. So in this case, this is a memory, so this is a synaptome, not a neuron. But a neuron is something that just spikes, right? The spiking can be achieved by vanadium oxide. So vanadium oxide, because it isn't just, okay, the naive explanation is that you have this metal insulated transition. You have a device with two contacts, you apply voltage. When you apply voltage, you have a current, that current heats up the material, and then the material heats above the transition temperature, it becomes metallic. When it becomes metallic, there is a spike in the resistance, right? Because now it jumps directly to the resistance of the high temperature phase. So in that sense, it's a spike, as in the neuromorphic. But there is more to think about it. So because what we have proved is that we can actually, as in the brain, like the thing you said, so integrated and fired. So it means that it integrates. It remembers that it was fired before, and then the next firing occurs to a lower threshold value. That's how the neurons works. We have proved that actually in vanadium oxide. Not in this, because this is different. This is a synaptome, not
It's binary.
Yes, exactly. Yes. So we have explored that with the different materials: vanadium oxides, VFO, niobium oxides, and now we are kind of into the manganites for some other reasons.
Yeah, thank you very much.
Sure.
For that.
Well, thank you for the very nice talk. I'm just asking that because at the beginning of the talk, you said that you made a coherent diffraction image.
You are the synchrotron guy.
Yeah.
You want me? Yes.
This image, right?
That one here, yes, that took a lot of pain to do that. Yeah. That's why I always find an excuse to show it. Just a second. Is it moved? Not moved. Yes, go ahead. What is the question?
Right. This is a Bragg coherent image.
Yeah, Bragg CDI.
Yeah. Okay. So I like this technique a lot, but I haven't trouble to perform this technique with real materials because I can't make the material stable enough under the pressure of that trading.
Okay.
How did you do that?
So, okay, I can tell you what is the idea behind. Maybe you can actually succeed. So we use these membranes, silicon nitride membrane. So we use a cement. We can mix this is a particle that has 100 nanometers. So we have this more or less monodispersed. We mix the cement with the nanoparticles in a particular concentration that is not very big, and then we put the cement in the silicon nitride, and then we have the postdoc in the night shift going through the whole membrane, finding a particle that actually was in the right size to give the fringes that we needed. But the trick is basically is the dispersion. I mean, if you put a bunch of them, then it will be hard to find. But according to him, it was just like an hour or so to find a couple particles that kind of work. But that wasn't the idea. The idea was that once you have the particle, and then we put on top of it, I forgot to say that, we put a contact on top of the silicon nitride and at the bottom. Okay, so the whole machine was doing transmission. But we put some contacts. We calculate how much we will have in order to have enough X-rays going through. And then we apply voltage. And what I want to see is the deformation of that guy by voltage. And the idea was, and this is, I haven't seen anybody trying this, is that you can, now you can change by 180 degrees your beam. So you flip the sample. And then by subtracting these two intensities, somehow you get information about the polarization. So if you work out the math, you will see that you can get rid of a bunch of terms, and then you get just the term that depends on the polarization. And what I wanted to see is the map of the atomic polarization distribution inside the particle. We did see something. We actually saw domains between the particle, but we couldn't understand why. And then we we haven't published that. So that is unpublished. If you want to talk about that more, I can.
Okay, thank you.
More questions? Questions and comments? No, if not, let's think one.
Thank you.